Today I will talk about the implications of strict exogeneity, which we covered in the previous video. One important implication is that there is no systematic error. Now, this means that on average, our linear model is correct. There is no systematic over or understatement of a dependent variable using the k independent variables and the constant term. We can state the following based on the law of total expectation. So the expected value of the error term vector given the data matrix is equal to the zero vector. We have discussed that, so this is simply based on strict exogeneity. Now I can apply the expected value on both sides. On the right hand side anyway, it's a constant, so it does not affect anything. On the left hand side, we have to consider the law of total expectations, which we covered in a previous session. So I take the expected value of the expected value of the error term given the data matrix. Thus, equation 1 states for every I, starting from 1, 2, going all the way up to capital N, that the expected value of epsilon I is equal to 0. Now we can easily see that because we know the value of this term, which is equal to 0 based on strict exogeneity. So we end up with a condition that the expected value of epsilon is equal to the all zero vector. Now this of course means, if you write this out more explicitly, that if I look at individual epsilon i's, that each and every error term running from 1, 2 up to capital N has an expected value of 0. So we could regard each error term as a random variable for the time being. To proceed, we need to establish that the expectations operator is a so-called linear operator. Now, when it comes to the property of a linear operator, what exactly do we mean by that? Say that capital X and capital Y, they are both random variables. And then we have constants A, B, and they are just real numbers. Now, what does it mean to say we have a linear operator? It basically means the following. You can take an expected value of, say, A times X plus B times Y, and I can take the expected value of the terms step by step. So the sum, I can just split it. The sum is simply split as ax plus. And then I can also move these constants out. So I can write something like following plus b expected value of y. You can formally show this. Yeah, so that's quite easy to do if you go back to the way we calculate expected values, using the integral or using the sum over all possible outcomes. I leave it there. If you want me to discuss this further, just leave a comment. Okay, next, it might be useful to understand so-called dot products. They pop up quite a bit if you go more into geometry or linear algebra. Most likely you came across it in school. Now a dot product works as follows. So we have two column vectors, and of course a column vector gives you also a position in, say, an m-dimensional space, if you have a dimension of m. So if you have only 2 dimensions, so we live in flatland, y, that's x, for instance, and we just have a dot here, I can always discuss the position of a point in this space using the coordinates. So in this case, it might be, say, a y1, x1, and that would give me the position of this particular point and also the associated vector starting from the origin. Now the idea of a dot product is I look at 2 vectors. So again, that could be in flatland, so maybe this one and that one here. So this is u and this is whatever v. And I can use the dot product to discuss how these vectors are positioned. So that's fundamentally the idea. So before we proceed, it might be useful to recall how to calculate dot products. So we look at two column vectors. I just say this is my A vector dot, so times the B vector, where this is now the dot product. Now, looking at this, it might be A1, A2, and we go up to, say, A small m. So we have an m times 1 dimensional column vector. We use the dot product here, and we have here B1, B2, all the way up to Bm. So again, we have a matching dimension. And the dot product simply proceeds as follows. We take now the A1 times the B1 plus A2 times B2 plus AM BM. Yeah, so that's basically the definition of it, and now we can use it. And it's also quite nice to use dot products when we work with column vectors, because sometimes it makes it easier to write down certain operations. I give you an example. So for instance, we could look at the sum starting from I from 1 to m of AI, where AI could be stored in this column vector here. So of course I can simply sum it up, A1 plus A2, blah, 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 up to AM. So that's perfectly fine. I could also write this as a dot product. Yeah, so I can simply say, okay, let's take A vector times the all-one vector using an all-one vector that matches in terms of my dimensions. Yeah, I can also, of course, switch that around if I wish, because it doesn't affect the outcome. So this you actually see quite a lot in econometrics. So have that in mind. It's quite nice and useful. Now we just use the same principle and we consider the dot product of the error term, so the column vector with dimension n times 1, and the all-one column vector with dimension n times 1. And we see what happens. Note that the all-one column vector is a column in the data matrix. We know that because it's associated with our constant term. Good, let's just simply write this down and see what's going on there. So I take the epsilon vector times the all-one vector, and now we notice that here it's n times 1 and n times 1. And what we actually get is we get epsilon 1 times 1, we skip the 1, plus epsilon 2, and so on and so on, up to epsilon n. And if we want to simplify this, we actually get what you saw just above. We obtain the sum starting from 1 up to capital N of the epsilon i's. So yeah, that's interesting. Now the question is, what's the value of this? Can we say anything about this? So that might be an interesting question to ask. We already notice that there is a little relationship to an expected value. Now it depends again how you view these random variables, but you could, for instance, view them as a realization of one random variable n times. So the idea would be, okay, I have a random variable, I call this epsilon, and I look now at a sample of capital N so-called realizations of this error term. And if I then want to calculate an expected value empirically, so this is an empirical assessment of the expected value of this epsilon, which now would be measured using my n realizations, I would simply do something like this. I just take the average of the stuff I observe. Yeah, so these are things I actually observe, realizations. We later will be a little bit more, precise about notations. So for the time being, I'm a little bit sloppy here. I'll just leave it here. So later we will talk about this being a realization, something we actually observe. Because again, have in mind, the error term is nothing we actually observe. We later talk about so-called residuals, things we actually observe, the errors we actually observe in our model. So that's a kind of a realization, it's a residual, and then we could refer back to this equation here. So you see actually that in the end, this here, this dot product is related to this expression if we view it in this particular way. Yeah, we already know, of course, that based on our discussion that the expected value of all these individual terms here will be equal to 0. And we also know that we could, of course, entirely use the fact that our expected value is a linear operator. So if you take an expected value of an expression like this one here, do it on both sides, and of course here again you have total, doesn't change anything because we don't have any conditions, nothing. On this side here, this is of course a constant. We can move an expected value inside, and we certainly know that this here is equal to 0. Yeah, so we know that this should be equal to 0, and basically, of course, that implies that this is equal to 0. Now, what that means is that the dot product of these two vectors is equal to 0. Now, this has implications in terms of geometry. That actually means that these vectors are perpendicular or orthogonal. So if you want to visualize it in 2 dimensions, you would basically now assume that these vectors here and this vector there, of course now this is not exactly what we have because we have 5 dimensions, that you have here a right angle between them. And that's basically what the dot product equal to 0 means. Now the interesting question you might ask is, now what can we say about all the other columns of the data matrix? And it might be now interesting to actually write down the data matrix in a slightly different way. You also call this a so-called partition. So looking at the data matrix, we know that we usually use the first column vector is the all1 vector. And then you have the vector for the first independent variable, and then we continue up to k, and we could partition the data matrix like this. Now all of these vectors have dimensions n times 1, so these are all column vectors, yeah, all of them, and of course you have k plus 1 columns, yeah, so we have of course the expected dimension for the data matrix. Can we say anything about the expected value of my error term and one of these independent variables? So that's an interesting question to ask. Now what you can do is, using the law of total expectations, you can just simply write this as an expected value of the expected value of epsilon I xit given the data matrix. Looking at this partition, we argued once we observe the data matrix, well, we also observe these individual columns. Now, if this is the case, we could treat this like a constant term. So if we want, we can proceed as follows. We can just simply take this out of the expected value because, well, it is observed, and write here the expected value of epsilon I given x. And that already we know is equal to 0. And we are done here. So again, we use here the fact that our expected value is a linear operator. So this is why we can do this operation. Looking at this, it basically means that our assumption about strict exogeneity implies orthogonal relationships, as the dot products are all equal to 0. Again, you might not have noticed, but this expression here, the expected value expression, is actually, of course, related again to the dot product in a similar way. Looking at the covariance, so if I look at the covariance of these epsilon i's, ij, I know, just writing down the formula for the covariance, which you certainly covered at one point in secondary school, that this is the expected value of epsilon I x ij minus the expected value of the separate terms, that this is equal to 0, so the term here in the back is equal to 0. We know this term here, we just argued it is equal to 0, so we know the covariance is equal to 0. So put differently, there is no correlation between the error term and the independent variables, because we also know if you look at the correlation of these terms, it's of course related to the covariance of these two terms divided by the standard errors, yeah, something like this. And we have to talk about this later a little bit more, and the various standard errors we get from our independent variables. So in summary, the strict exogeneity assumption has several implications. Basically, our model is on average correct. There is no systematic error, and we cannot predict errors knowing any of the independent variables.